Hi, I'm Elisa, and we're talking about the nervous system. So, now we're going to get into an introduction regarding the electrochemical signaling used by the nerves. Electrophysiology is the study of how cells, specifically neurons in this case, are going to produce electric-like signaling. So, it's the basis for all neural communication outside of things like neurotransmitters and all that, and muscle contraction as well. It requires an electrical potential, meaning stored energy. And that stored energy is the difference in the electrical charge or electrical charge, or also known as the electrical gradient between one point and another. Again, it's a type of potential energy. And what's interesting is since it's electrical like, we measure it in volts. And it causes an electrical current to flow between 2 points very quickly, which is one of the reasons we like it for communication. We also need to talk about the idea of what membrane potential is. It means the membrane has to be ready to send that signal. So we look at it as being caused by the separation of charge between the ions. It means there's got to be some positive ions on the side and some negative ions on the other, something that's really tense. So when we disrupt it, we can send a wave, a pulse of these ions streaming across the membrane. So inside the membrane, it's always going to be negative, at least negative relative to the outside of the membrane. And the average resting membrane potential is going to be so negative, it's at about negative 70, but millivolts, because these cells are small. An electrical current. So think of it as the flow of charged particles. So like when you think of electricity, it's the flow of electrons over distance and time. So it's a current, kind of like a current on maybe a river or stream, except for water, it's charged particles. So we're going to use something a little bit different from electrons. They're a bit bigger, they're ions, but still same idea. An electric current is caused by a difference in electrical potential or voltage between these 2 points, usually meaning negative and positive. Charged particles will flow down an electrical gradient. They like to balance each other. So the ions we're going to look at are sodium, potassium, calcium, chlorine, etc. These are going to be these charge carriers. As you can see, they all have either positives or negatives. They're charged ions. In cells, electrical currents are due to the movements of these ions through channels. They're like little gates in the plasma membrane. They control who goes in and who goes out and how much. These gated channels are guarded. Now those can open and close to control this ionic current from going in and out. Resting membrane potential. We can also call this the RMP. So it's an electrical gradient, or we refer to as the voltage, right? That's how we would measure it, across a membrane when a neuron's just sitting there resting, when it's not exciting or talking to any other neurons. Inside of that membrane, again, it's going to be a little negatively charged relative to the outside. So the resting membrane potential exists because these ions are not equally distributed, right? There's too many positives on one side, too many negatives on the other. It means they're tense, kind of like magnets. They want to stick together. And as soon as that membrane's out of the way, they're going to do that. So the membrane is selective about certain ions. Some of these channels have either gates that are very specific to certain ions, or maybe they're only shaped to allow certain ions to pass through. Maybe they only allow really tiny ones, stuff like that. That's the selectivity. So we know that these ion channels are selectively permeable. So that means potassium channels only are going to let potassium through, and sodium channels are only going to allow sodium through, and so on and so on. Ionic current through open channels is determined by things like the ion concentration gradient. So concentration means like how much of something there is, and the gradient means like how stacked up and pressurized it is. So if there's a lot of it, it means we're going to have a pretty busy and high flow current. If there's not too many of those ions that want to come in, it means it's going to be a slower current. Ions are going to diffuse across the membrane based on just the properties that positives like to go where negatives are, and vice versa. So, electrical gradient, meaning that membrane potential. So cations, remember cat, like pause, positive. So here we have sodium and potassium are positive, are attracted to all of that negativity on the inside of the membrane. So they tend to stack up on the outside. The resting membrane potential, also known as the RMP, right? So potassium is going to have the greatest influence on the charge gradient across the membrane, right? So the thing is potassium is 40 times more concentrated on the inside of the cell than on the outside of the cell. There's just a ton of potassium on the inside of these axons. So the cell membrane is more permeable also to potassium than other anions. And the reason is because these potassium channels are always kind of leaky. They're always kind of open. And so all of these little positive potassium ions are attracted to all of the negativity on the inside of an axon, right? So as the potassium starts leaking out, right, and moving out towards the surface, what ends up happening is all of these giant negative anions have to stay behind. And that means that, where is it? The membrane becomes more negative on the inside, okay? And it's kind of interesting because that same negativity that they left behind is what attracts them back in, right? So eventually equilibrium is reached because of this back and forth play. So there's no real net movement of the potassium, right? It occurs when a tendency for the potassium to exit down its concentration gradient is equal to the tendency for the potassium to go back in or to enter, which is down the electrical gradient. The electrical gradient across the membrane at equilibrium forms the basis for all of this resting membrane potential. It means that it's a little more negative on the inside. It's waiting for a positive change to kind of bump and change the membrane potential on either side, thus sending that propagation on the way down. So, membranes, they're not very permeable to some of these bigger ions, like sodium, right? So, when we're at rest, the resting membrane potential is kind of influenced by it. So, sodium is about 12 times as concentrated in the outside or the extracellular fluid as compared to the inside. So you could think of it as all right, here's our little axon, and here's our negative, right? And here's our little sodiums, these giant sodiums. Okay, and so they're kind of being always pulled like magnets to the arm, right, of this axon. And so that's why they're always sitting there, and that's why they're concentrated 12 times more than normal, okay? So when some of this sodium leaks into the cell, it's I finally get to be where all these negative cations are. What ends up happening is we start disrupting the membrane potential between the two of these, and we start making this a little less negative. So it means that we're employing the sodium-potassium pumps. So the important thing to know about a sodium-potassium pump is it kind of does this thing where I always kind of envision it, well, I think a lot of people do. Here's the membrane, right? Here's the terrible handwriting. Oh my goodness. I have to just kind of try. There we go. And so what these channels do is they'll reach up and they'll grab sodium and potassium and move them either out or in one fell swoop, in one fell motion. So that's the pump. It requires ATP to execute this function. So as sodium is now moving out of the cell, it brings all this potassium back into the cell. And that helps create and maintain that sodium-potassium ion concentration gradient across the membrane. It works all the time as long as we have ATP. And the thing of it is it's really expensive. So most of that sugar that your brain's eating is going to go straight to the manufacture of this ATP. It's actually about 70% of the energy work requirement. So a little better image would be this one. So here is a sodium channel letting in the sodium. Here's that leaky potassium letting it out. And then all the time we have these bigger negative right? Anions. Remember, cations are positive and anions are negative, right? So like think cat ions, like cats have paws, so positive, right? And so anions, those are always just going to be the opposite, which is negative. All right. So that is the basis for resting membrane potential. And the reason why I want to go over that is because it's a little bit confusing with all these positive charges being the real movers. So they're really just reacting. And so resting membrane potential means that this is just how it is all the time when it's waiting. And so when we get an impulse, an incoming impulse from an adjacent cell, it's usually going to alter the external, right, this extracellular fluid, and we're going to change the balance. And so that's going to cause them to kind of start switching sides, if that makes sense. Okay, so we'll look at this a little more closely, but I just wanted to get some of those basics in. All right, I hope that was helpful, and we'll see you later.